the energy resources that we'll be taking advantage is primarily what are hidden on the ground. We call them subterranean resources. Now, when you go to the solar and wind, you're talking about above ground. So let's take a look at what do we have underground that has been running the lifestyle we have for the last, I would say, several hundred years, basically, and now it has changed over the years. In this category, I am including oil, gas, coal, and geothermal. And we'll see how these things are formed and how they're used. It was discussed this morning that among the top 10 problems we're going to face during the next decade, actually, energy is number one because it affects everything else, even for water purification, for food processing, for environmental cleanup. All of that really depends on availability of cheap supplies of energy. And as was mentioned by Dr. Don Paul, part of the problem is the growth in the population and the demand that the additional population is going to create. And so we got to start thinking about potential solutions. I want you to pay attention to this diagram. This diagram shows you from almost 1800 to today what have been the drivers that we have switched from one form of energy to the other. Now, you all have heard about biomass. You know what biomass is? What's biomass? Like burning wood, right? As you know, in this time, it was the biomass that actually, have you seen those old movies, the locomotives? Basically they were burning wood to drive the locomotive. It's funny that after all of these, we're going back to the cycle of the biomass. People are talking about just burn wood rather than burning more. I want you to know, anytime you burn anything, whether it's oil, gas, biomass, coal, you're going to generate CO2. People talk about, for instance, biofuel. We're going to have some discussion on that. Even in biofuel, when you burn ethanol, what are you going to do? You're going to generate CO2. So there's no way you can get away from not generating CO2. But I want you to take a look at there's a major change that happened over here. Where's the pointer? Is there a pointer here? Is there a pointer?
Yeah, it's
you don't have a pointer. Oh, yeah, I can do it over here. Can you see my mouse? Right? Yes. Yeah. Take a look over here, the air travel. Just think about it for a minute. If it wasn't for the availability of liquid fuel, we would not have had the air travel. If we did not have the air travel, probably most of us would not have been here today. Just imagine how it changed the lifestyle we have, how it made it easy for people to travel, go from different places. And all of that because we ended up having jet fuel as a byproduct of petroleum that made that possible. So if for any reason we want to go ahead with alternatives, we have to keep in mind that it's not just the automobile, it's not just the way you heat your home, it has to do with also the transportation above the ground. We talk about helicopters, we talk about like that. What are you going to do? What are the alternatives? Nuclear fuel, I think you're going to have a lot of opposition to put nuclear fuel for air travel. Most people will not get on an airplane, so there's psychology also about that. So there have been certain triggers here throughout the history that have necessitated that we use different types of fuel and coming out where we are. Now, all of a sudden, if you begin to look at the energy use, you can see how it skyrocketed, went up, and who knows where it's going to be heading. If you just go based on the population, you might be heading over here. And the only way you can do, perhaps, to slow this thing would be maybe through some conservation measure, or maybe through some kind of a price increase. It's interesting. When the prices go up, the consumption goes up. Okay? And in fact, some people have promoted that idea, that one way to cut the consumption in the U.S. is to increase the price. Of course, you do that, you're not going to get elected to any office in the U.S. But if you do that, the difference perhaps could be used for investing in other forms of research and development that we need. Now, over here, as many of you take part in chemistry, you know that you look at the composition of methane, I showed you was carbon and 4 hydrogen. You look at oil, you got a whole bunch of carbons and hydrogen. Look at the coal, there's a lot of carbon, very little hydrogen. And so it's really the combination of whether the hydrogen over carbon ratio is less than 1 or more than 1 or a large. For instance, when you look at the wood, biomass, and coal, hydrogen over carbon is less than 1. And as you can see, from 1850 to 1900, we were using fuel that had hydrogen over carbon less than 1. So basically, if you look at the burial of plants, that they were decayed and ended up to become coal, it happened that during this process, it lost its hydrogen. Coal doesn't have much hydrogen left in it, so you end up with nothing but carbon. And you got to do something with that carbon to be able to use it. And it turns out that many of the processes requires actually adding hydrogen to the coal. Now you go to the oil. Oil is in a situation where the hydrogen over carbon is roughly equal, but in fact 2 to 1, sometimes even 1 to 1, depending on what we have. Now you look at the natural gas. You go, for instance, go to the hydrogen economy. You're talking about a system where the hydrogen over carbon is more than 4. So if you look at the colors, you can see that as the use of the fuels that had a hydrogen over carbon less than 1 went down, gradually the type of the fuel that hydrogen over carbon more than 2 or equal to 2 went up. And of course, gradually also we see a buildup of the fuels that have hydrogen over carbon more than 4. You see something very interesting, and that's a shortage of hydrogen. If we were able to come up with an inexpensive way to generate hydrogen, we would have come up with a very clever way to solve our energy problem. But the Mother Nature is very tricky. Doesn't let you do that. You could use energy to break seawater and generate hydrogen, right? But then you say, where do I get that energy? It's kind of this vicious circle. So you have to come up with, some people promote use nuclear energy to generate electricity, use the electricity, the seawater, generate hydrogen, use that hydrogen for various purposes. Well, it will only become economic. And for instance, you've heard about fuel cell. We're going to have a discussion later on. The whole idea of the fuel cell is that you're able to generate hydrogen and use the hydrogen as a fuel. But then that hydrogen has either to come from water or methane. If the hydrogen comes from methane, now, as the cost of methane goes up, which is natural gas, the cost of hydrogen will go up. So there's no easy way. I mean, there are certain things that technologically are possible, but it still is a lot of research to try to fix it so we be able to afford it economically. Now, this was mentioned because we're going to need this number. So it was mentioned this morning that the U.S. consumption of energy roughly is 100 quadrillion BTU, which is about 3 terawatts. World is 4 times. Okay? 400 quadrillion for the whole world. Now I want you to take a look here that if we wanted to satisfy this 3.3 terawatt energy that we need from other sources, what do we need? Let me go back first of all to that. Notice for the US, 3 terawatt.
Okay.
Okay?
Wait, what?
If you want to have 3 terawatt,
105.
you need to build 3,300 new nuclear power plants, one of each 1 gigawatt. That means you need to build 100 reactors every year for the next 30 years. Easy thing to do, right? That's easy to do?
No.
Yes, no,
Not at all.
it must be impossible. So, biomass. Suppose we go plant trees, and we harvest the trees, and we use it to burn and generate. You're going to need 2,280,000 square miles of land to do that. And if you want to find out what does that mean, take a look at that next table. The entire world, the land area, is 196 million square miles. If you kick people, everybody out, throw them into the ocean. If you look at Australia, I think I had it here. Australia is roughly 2,968,000. So that means if we can get rid of the people in Australia, you have enough biomass outside. The reason this is important is because it's easy to talk things that are very appealing, but you actually have to do the calculation. Now, let's go on to population. I've put a few countries that have large population density. Basically, look at Bangladesh, 144 million, Pakistan, 162. India is going to be a little higher than that, 1 billion more. Germany, 82. Japan, I put it for a purpose here, because I want to have numbers to add up. If you add up all of these people, all of these countries become about 2.9 billion people. The population in the U.S. at the time I did that was 295. So you know why I selected those countries. 295 is 1/10 of the 2.9 billion, right? So population of the U.S., 1/10 of all of those countries, the energy we use is equal to the energy that they use.
Oh my gosh. Oh my gosh.
Got the message now? So you know where the problem is. Because the lifestyle that we have here is such that it requires that amount of energy. Either we have to substantially reduce the convenience that we've had and enjoyed and just live like the rest of the world. Or we tell the rest of the world, you have no right to live like the way we do. So then that's kind of
No.
Or we have to come up with our economical sources of energy to be able to survive. It's important for you to know these numbers. Now, one of the interesting problems in the business of energy has been the price. Look at the price of every commodity you have has been increasing. The price you pay for rice, egg, coffee. The price of energy has been fluctuating. Okay, you have different events since, say 1969, I'm sorry, from 1861 to 69, going all the way to present. And you can see how it has affected the price of oil, for instance. Crude oil prices since 1861. Now, if you look at basically when we discovered oil in the liquid form in Pennsylvania, going all the way down to the Iraq situation, you can see how much this is going up and down. Why? Well, part of that has to do with panic. For instance, in 1969, when there was the Iranian Revolution, there was a panic in this country. Everybody thought, gosh, we're not going to have any more oil coming here. The price of oil went up from $12 to $30. And there was nothing out there. All the tankers were coming. Just that perception that we're going to have a problem raised the price of oil. Probably many of you were not born in 1979. But you could ask your parents. The situation was that you have to go in line to the gas station almost at 5 o'clock in the morning. You had big lines to get gas. People would come on and fight with each other. 5 o'clock in the morning. I was earlier than you were earlier than me. People would go at night, siphon gasoline from people's cars. And many people died because of that. They didn't realize that gasoline is toxic. Because if by 9 o'clock you didn't get gas, the gas station was closed, they were out. And you were out there, you can't go to work. Okay? It was panic. Unnecessary panic. 1973, prior to that, we had a similar situation. And so, once these things happened, which has nothing to do really with what's happening in the U.S., it raises the price of oil, creates panic, and people overreact. Now, part of the problem is that, part of the problem in recent years, we heard about this $150 oil that was happening last year or so. It has to do with the people who actually make money because of future trading. In other words, I come to you and says that, listen, right now the price of oil is 70, I guarantee to pay you 70 for the next 5 years. You guarantee you're not going to charge me anymore. And, you're an opportunistic purchaser. That's great because I know price is going to go up. So you do hedging. And this type of dealing has nothing to do with the energy supply and demand. Sometimes raises the price of oil, drops the price of oil. But if you eliminate all of that, we are getting now to a point where truly the supply and demand are working against each other. In other words, we always had this slack. We had a certain amount of excess per capacity that if the price basically goes up, we can flood the market and the price will down. We are getting to the point we don't have that anymore. So unless we come up with some quick solutions, from now on, if we have any type of panic or disturbance, the prices are going to go up. So enjoy the gasoline as much as you can right now, okay? Not this week, of course, yes?
I'm just wondering, is that graph in real dollars or?
No, it's just basically to the dollar, it says a given year. I don't know if it was 1980 or 1970. No, it's relative, right?
What's the orange line and the green
Okay,
line? Guessing the orange line is
there are two things that we're demonstrating over here. One is the actual price at the time. One is when it's normalized to a given year. I don't have the year here. I think it was either 80 or 70. The green one actually the green one is normalized. In other words, can you imagine if you take, for instance, the price of oil at this time was about, say, $5. The $5 of that day is equivalent to a $90 of today.
That makes more sense.
See that?
Oh, okay.
Right.
So one's real
For
dollars.
instance, when you go to the Iraq situation was about 1991. So if you go to 1991, you see that green one went up there? It was $80. In reality, it was only $30, okay? But it was equivalent to today's price of $80. So, you know, today we are paying less for oil than we did in, say, 90. But you can see this spikes, they cause problem. Okay, Dr. Sheen probably talked about this, that we take advantage of every molecule that comes in a barrel of oil. A typical barrel, one barrel is actually 42 gallons. You get about roughly half of it you convert it to gasoline. And then, of course, about 4 gallons for jet fuel and the kerosene, and of course, some would go for petrochemical. The leftover becomes asphalt. So we don't waste any. What that means is the following: if I own a refinery, by the way, many of our graduates in California now are buying the small refineries, operating it. If I own a refinery, I look at where the market is, and I could adjust things that I make more gasoline or more jet fuel. Okay? If the crude oil that goes to the refinery is what we call a good quality crude. California crude is a low quality crude, it's heavy oil. Texas crude, 36 gravity, it's good. Alaska crude is good. What that means is that you can generate more percentages of gasoline or jet fuel from light crude than with the heavy crude. So we have the option how we distribute that depending on what the demand is going to be. But if you think very carefully now, I want you to do this calculation in your head. It's fairly easy. Suppose the price of oil is $50 per barrel. Okay, just remember that $50, although it's right now fluctuating. So that means for 42 gallons of this crude oil, at the wellhead, let's say you're paying $50. When this thing comes to the refinery, you're getting what? You're getting about half gasoline, right? 20 gallons of gasoline, right? The rest of it is used for other purposes. You take that 20 gallon and through either a tanker or through a pipeline, you send it to the market. So you can see that if you take the $50 that you have and then looking at it, that the gasoline that came out of it was half, you can actually calculate what the cost of that gasoline per gallon is. And then roughly if you divide, say, 50 by 42, it becomes like a $1 per gallon. Because that's the gallon that has become a gasoline. So $1 is for gasoline. And when the price is $50, $1 per gallon is the actual cost. If you don't do anything. Of course, you've done a lot of things to convert the crude oil to gasoline. If you put all of that to be roughly about 50 cents per gallon, so that's $1.50. The refineries, for their own profit and everything else, they have about 15 to 20 cents margin, basically. So that brings it up to about $1.70. So why are they charging $2, $3? Because we have close to $1 tax. Okay? And of course, in California, we can't use the gasoline they use in Texas because of the air quality standards. So we add some additional thing. As a result, the California gasoline is much more expensive. And the gas station owners actually don't make much money. Their margin is about 5 cents. So if the gasoline price goes up, they're not making much money. It's the cost of the crude. If the crude goes down, gasoline comes down. So it's the taxes and the cost of the crude. The rest of it is not really very much. So if right now you say, how come the prices are not $1.60? It just can't happen. Mathematically, it's not going to work out. Now, we were talking about subterranean resources. This oil and gas and things that we talk about are really in the crust of the earth, which is a very thin layer. The rest of the earth, when we go to the mantle and the outer core, this is a very high temperature environment. Oil and gas and everything is not going to last over there with that temperature. But later on, I'm going to talk about geothermal, and you can see how we take advantage of that heat inside the earth as a source of energy. So right now, my focus is on the crust. Now, all of you have had it in elementary schools or in science courses about how the fossil fuel, such as oil, coal, and natural gas were formed. Historically, basically, you have sea plants and animals that they died, they were buried, they were covered, with sediments, clays, and under the burial, the weight of the sediments, they were decomposed, the bacterial action, eventually we went from stage 1 to the last stage where you ended up with this oil and gas deposit. So when we actually go, we drill a hole to find those deposits, we don't find a pool, a swimming pool full of oil. We find very tight rocks, and you find this oil and gas in the pore spaces. This is the kind of rock we produce. Can you imagine? In between the pores here, that are usually about maybe 50 micron, we produce oil. That's what it is. Now, of course, this thing is clean, but if this was hydrocarbon bearing, it could be kind of a brownish color. Now, I put here, for example, this is the rock. If you smell it, you smell like hydrocarbon. This is the one that we call the Monterey Formation. In fact, if you have the match over here, you can burn this. This is tar. This is the fractured rock. Many parts of the world you can find fractured rock, but there is nothing in the rock, it's in the fractures. Okay? So sometimes we drill into these rocks. Now, most of the rocks we deal with are extremely tight. It's just a matter of being able to find the rock, making sure there is hydrocarbon, then bringing it up. How do we do that? Now, how do I find these rocks? Well, these are surface rocks. The same rocks you have in the reservoir, sometimes they outcrop, so by sampling them, I know what's in the reservoir. But in many cases, I don't have that. So the only way I know what these rocks look like, we drill a hole, we go down there, we take a sample to look at it. You get enough training to find out. We look through microscope, we do all the analysis to find out what the pore space is, what kind of hydrogen we have, and how best we can move this oil out. Oil is a very lazy substance. It doesn't want to move. So if you get to this, it doesn't want to come up. Okay? So it has been a fight, the scientific fight to get that oil out. We trick it. For instance, we use partly the dissolved gas that in most situations you find. It's just like a bottle of Coke. If you shake it, you can see the gas brings the Coke out. Same thing. The gas that's dissolved in the oil, it helps to bring some of the oil out, but not all of it. If you just depend on that gas, you only get 15% of the oil out. There are many fields in the U.S. that they still have 85% of oil left, but the oil doesn't want to come out. The oil is sitting there. Somebody was asking, how come we don't go after an oil field? People are going after those fields that have still 85% there. They try to use all kinds of chemistry concept. The way we trick it is that, oil and water don't mix, right? If my hands are oily, how do I clean it? Oil. Not with water. Water and soap, right? Soap is a surfactant, so it doesn't cause oil to be dissolved in the water. Basically, what it does, it breaks the oil into small droplets that are easily removable. So if we use the terminology, it solubilizes the oil. Then we have in a reservoir, we inject water that has been very carefully, the chemistry has been adjusted, and it's different. Every field is different. And we add, not soap, you can't use it. We use surfactants that are designed for that. And actually, when this water and chemical go there, the oil that's sitting there feels there's a solvent coming. You know what a solvent is? Like a nail polish remover. That's a solvent. If you could afford to inject toluene or acetone in the reservoir, you would clean the reservoir. But we can't afford it because those stuff are more expensive than oil. So what we do is we inject the water with these chemicals, and then the oil thinks there's a solvent coming, it starts moving. And if you're successful, you can get a lot of oil out. Okay? And we are doing it in some cases. In most cases, the reason people haven't done it is because of this fluctuation of price of oil, or sometimes the cost of surfactant is more than the cost, price of oil. So when the prices become stable, then people go back to these things here. Is that the end of it? No, because you find out that one of the jobs that reservoir engineers do, it was mentioned this morning, is that for every oil field, like a human being, is a different interpretation. You need to take a look at, you can take all kinds of imagery of this reservoir, rock analysis, sample analysis to find out what kind of a treatment is necessary. By the way, I should show you this rock. You know, there's a place in California called Solvang. Have you heard about it? You probably didn't know that close to that area, there is a quarry that they quarry a rock, which is called this. This is diatomite. This rock is very light if you hold it. You know, in fact, you could go there, take pictures. You can take a boulder that big, you can just hold it in your finger. Now, when I was a kid, I was always impressed why Tarzan was able to do that, and I figured out it was going to solve that too. This rock has 70% porosity, and if you look at basically in some cases how much oil it contains, it's amazing. But there is no permeability, and there was it's full of oil, it doesn't come up. So we actually go down there, we hydraulically fracture this, you break it, you know, it could be 5,000 feet, we break it, we fracture it, and we get the oil out of it. Otherwise, you can't do that. So you can go ahead and pass it on. Of course, we have a paper towel here in hand. So we are dealing with very, very complex rock structures, out of which we're trying to extract oil. Now, sometimes we find these deposits onshore, sometimes we find it offshore. So for instance here, look at this definition here. We have the continental margin, the continental slope. You could find oil fields right here, over here, over here, over here. And how do we find them? Of course, I'll talk briefly about the methodologies. But we use every principle that you learn, fundamental thing you learn in chemistry and physics. It's only that. We use principles of physics to image. Have you seen CAT scan for a brain?
Yeah.
We use X-ray to scan the brain of an individual who may have a tumor or something, right? So we do exactly the same thing underground, except we don't use X-ray. X-rays cannot penetrate that deep. We use sound waves, and we image it. I'll show you an image. And we actually see where the structure is. Okay?
Oh.
Okay. Now, I'm going to make sure that Julie gives you a copy of this in a large size. This is a poster that was prepared by MMS. It's very nice because it shows you in one, oh my God. It shows you the geologic history, that how the sediments were formed, all the way to the tectonic forces that causes folding and arching of these sediments, faulting. And then it shows you how we use exploration to find out where these resources are, and then how we actually drill onshore or offshore to be able to get to these sediments. So in most cases, what you have on the ground could be a very complex structures like this. And it's our job to know exactly where we're drilling. It was mentioned by Dr. Paul this morning, or Warren Williams actually, that it could cost you in the order of $150 to $200 million per well. So you can't afford to risk. It's interesting. The people who really get excited by this concept are the drilling engineers who they use satellite dynamic positioning. You go in the middle of the water, you have nothing. You don't see a shoreline or anything. You exactly position where that well has to be drilled that will go down there and hit that oil site. That's amazing. Okay? There's a lot of high tech is used to do that. As a matter of fact, not only that, now you're able to do it from remote distance. You can sit in a New Orleans office and actually position where that drill ship has to go to drill exactly in that location so you don't miss it. Now, after we drill the well, you probably have seen these pumping units all over California. Then you basically produce for a while naturally, and then of course when the pressure goes down, you put these pumping units that create suction, you bring oil to the surface, and you treat it. And in some cases, if the oil is very heavy, as I mentioned, you might be injecting a fluid. One of the fluids we inject is the steam, high temperature water, we inject, and that steam actually helps to push the oil out. But again, the application and the design is different for each reservoir. If you go to Bakersfield area, majority of the well, we have about 25,000 wells over there. Majority of them are producing that. Now, offshore becomes an issue. So if the water depth is shallow, we can actually put a structure about 1,000 feet, 2,000 feet. You just have to think how difficult it is to put a tower that would sit on the ocean floor here that would be in a water depth of 2,000. You got the force of the wave and the water pushing this thing over here. By the way, if you go on the YouTube, you'll find out some examples, because it takes 6 or 7 months to build this thing. You tow it, you bring it to the place that you want with a barge, and then at the time you want to put it, you make a mistake, it goes upside down, you've lost the structure. And if you have to put it in such a way that it just sits right there. So there are actually movies you can watch how they carefully place the structure to go sit over here, the legs, and then you. Now, if the water depth is much higher than that, you can do that. So then you have this floating structure. You drill from here, you go down here. As Warner mentioned, this water depth is increasing. We go into great depths. Now, gradually we're approaching 7,000 feet, which is more than a mile. Now they're going to about 2 miles, So that means you go about 10,000 or more feet, basically. And then from that here, you drill a well and you go find it. Just imagine how complex it is to locate exactly where that well is going to be. And I'm going to show you a little bit later on that in many cases, we actually right here, we branch off, we drill a well back here, another back here. We call this a multilateral. So there's one well that actually branches out to different areas. Now, later on, when this guy is done, we remove it and we complete the well on a seafloor. So you don't see anything on the surface anymore. Then with a series of robotics, actually, we have devices that come over here. They control this wellhead right on the ocean. You can set divers over here. Okay? This is all done remotely. In fact, one of the areas of research that our people are doing here at Stuff is sending signal to the water. Sending signal to the air is very easy, right? No problem. Sending signal to the water is difficult. So imagine you have you want to say yes, no. So 0, 1. And you want to send that somehow to the water. Go about maybe 100 miles to the shore, and the shore, somebody knows something is happening over here. So this is a very interesting area that people are focusing on. Underground, what we have, what we find in oil fields, geologically are exactly what is happening these days. Anything you see at the surface years ago was the same thing, it became an oil field. So we are learning from the recent geological processes. Lorraine will be giving a talk later on geology. In other words, by a study of what is happening today, we know what happened 400 million years ago, because nothing has changed in nature. It's the same rules that we have found. For instance, if you go to Palm Springs, Palm Desert, you find the sand dunes. Have you seen them? Sand dunes? No? Well, you gotta go there first. These sand dunes, basically, that existed 100 million years ago, they could be oil fields. And why is that important? Because we study the modern sand dunes and we understand what type of erosion we could have on the ground. Or the river deposits that you see today. This could have been the same thing 100 million years ago that became an oil field. So the oil fields of today are actually have the same geological conditions that is happening. So, of course, right now we're not forming oil because we live over here. But then at some point in time, there were no human beings or animals, anything on this planet. Anytime you get a big flood and you cover the land, and you could make this area susceptible to becoming an oil field. But that takes a long time, and not a lifetime, of course. Now, how do we find these deposits? Is through seismic. You may have heard that terminology. We use seismic on land and offshore. So here is a seismic boat that goes like this, almost like a zigzag, and it records the signals that are coming up. By recording the signal, we actually image what's on the ground. This is a technology called three-dimensional seismic. It uses the principle of physics, it uses the principle of mathematics to solve the Taylor equation, and of course, be able to do this thing in real time, be able to do the interpretation rapidly. This is how a seismic looks like. Yeah.
Have they ever made a mistake to know that there's nothing there?
It's a good question. The old technology, let's go real old. The real old technology was that you see some tar on the ground. You go to Santa Barbara on Polo Point, if you go next to the beach area, you see tar oozing out of the rock. Okay? That's how people find oil. It says, there's tar over here, it must be oozing out from someplace. So it was the surface indication of tar. Okay? But that wasn't enough. So people went drilled and they find oil. If you go on this campus, there is a library called the Doheny Library. You may have heard Doheny's name. Doheny was a person who was looking for oil in Los Angeles. And right around 3rd Street and another street in downtown, again, downtown wasn't the way it is right now. So they find an area that oil was oozing out. And he starts digging with hand. Not drilling, nothing. He starts digging it to the point it gets deeper and deeper, okay? And then they start using like a telegraph post. They start cutting the rock. In about 50 feet, he finds oil. He becomes rich. He became so rich that he donated a big library to us, and there are all kinds of things in his name. So there was a time you can find oil at the depths of 10, 15, 20 feet. Those days are gone. And of course, once he did that, people started drilling. If you go to the website of the Public Library of Los Angeles, you see some fascinating pictures, and sometime maybe you want to do a project on that. How did Los Angeles downtown look like? You see these derricks all over the place, almost like a jungle. So you would drill a well here, and you find oil, I'll come drill next to you. There was no seismic. And so the only way I could find out if it's the right place is that if I find oil, then it becomes part of this map. So most of the discovery was like this. And it was just and of course, once we had the seismic, things become easier. No. The seismic technology was such that we could only find where these structures were. But it couldn't tell us whether it has oil, water, or gas, or nothing. It doesn't tell you that, right? But today, the seismic technology has reached to the point. You see, you have to differentiate between oil and water. That's the whole issue. You're not looking for water. Okay? There must be something different between water and oil that you'll be able to detect it here. And it's interesting when you look at the properties of water and oil. The densities are a little bit different. Water is heavier than oil, right? Dielectric properties are different. Resistivities are different. So that's where we go to the physics. What makes water and oil different than gas? And now we managed to come up with a better way of interpreting. Today we can find gas. And if it's gas, I get a white spot, and I know there's gas in it. I still have problem finding the difference between oil and water. So the chances are that when you go offshore in those great depths of water and you find a structure, the chances are on the first well you still don't know if you find oil. So if the first well hits oil, then it allows you to go to drill more. Now, let me continue here. Part of it also has to do with the luck, part of it has to do with geology. I work in Vietnam, in the waters of Vietnam. Those guys find reservoirs that are so tiny. It's unbelievable. You go through all this expansion, you find a tiny reservoir. Then you go next year, you find another one. So now the technology that's used is one well going through the first field, and the same well with the second well, and with one horizontal hole, and try to drain 3 wells. Very expensive, right? You come to the Gulf of Mexico, you find huge reservoirs. Of course, after you discover that, then you say, I should have thought about the geological reason why Vietnamese fields are so small, why, for instance, in the Gulf of Mexico. So there are geologic reasons we're finding it. Yes, go ahead.
Okay. How would you interpret that?
Okay, so I like that question. Can I hand over to you?
Wait, press.
Okay, so what we have wrong thing, yellow. So let's imagine that you're here, and let's assume that underground and actually you have the geological layers that look like this. Okay? Let's assume there's a fault over here and fault over here like that. We like these structures. The structures that look like that, the chances are that there must be maybe something trapped. So what I do, this is the old technology, but I'll tell you how we've changed it. In old technology, I go over here, I drill a well that's about maybe 5 feet. I put a stick of dynamite over here. We don't do that anymore. And then I create a vibration. It's almost like a seismic. All of these things go down, they reflect back. Okay? Then I put recorders here. These recorders are almost like the devices we use these days to detect earthquake. They just record the vibration. And I have the same thing on this side. So there is a certain amount of time it takes for the signal to go down here, come back here. For this, it took longer. Why? Because this was a little deeper. And then the same thing happens here. Same thing happens here. So what I get at this recorder is what I get. I get like this, like this. At this recorder, I get like this, like this. At this recorder, I get like this, like this, like this. I connect this, connect this, connect this. This is the data. Okay. So when you look at that over here, essentially you're seeing there, these are the reflectors we have. Pretty flat over here. There are better images. You want to again Google image, just say seismic cross section. You see all types of cross section. So if you have trained eye, you can actually almost map that and so very well. Okay. Now I said we don't use dynamite anymore. So what we do is we drop a weight. So we have these big trucks. You go and they just drop a weight. They vibrate the ground. That's good enough. Yeah. Oh yeah. Now, these days we get these images. So that's a seismic image. You see the little one? We get these images. We project it in rooms like this. You can actually come here. So over here, see there are two engineers talking. This is where the wells were drilled. This is where the seismic is. So they decide where the next well is going to be. In other words, you kind of immerse yourself in the image. So there's a lot of work going on in geologic modeling, and it was taking those images, building three-dimensional rendering of what's on the ground, and then deciding where to drill the next one and how to develop that. These are some additional images that comes out of these type of systems. Now, in this, there was a question this morning, what do the engineers do for oil companies? You could become a specialized in the reservoir. This is the most respectable type of work because for lazy people especially. You don't do much traveling, you stay in a beautiful looking office. These are the most respected people because everybody depends on the reservoir. This is the most complicated. You do reservoir modeling, you do reservoir imaging, you do reservoir calculation. It's all in the comfort of your office. If you want to go out, you could go and talk to the drilling engineers, production engineers, and then of course you have the processing engineers, transportation engineers, all the way going to the refinery. But everybody depends on reservoir engineers. Okay? But of course, the reservoir engineers depend on the drilling engineers, and the drilling engineers that later on they have to go with the production engineers, then you have the surface facilities. These days we call this whole thing asset management. Now, what has happened is, because of the sensitivity of how the market demand affects things, for instance, if the price of gasoline, let's assume nobody wants gasoline. Tomorrow we wake up and say, we're not going to drive, right? So what happens is, we shouldn't be sending the oil to the refineries, right? So what's going to happen? That's going to affect here, I'm going to have to shut down the reservoir. Or on the contrary, if this reservoir develops a problem, it's going to affect the gas prices. So this is called an asset. Now, if you look at a complex system such as for the major companies, if you look at Chevron, remember they showed the map of the world, they have operations all over. So you have assets, Argentina, North Sea, California, Gulf of Mexico. How do you manage this? How do you make sure that everything is operating? Well, it used to be dependent on people. The Problem with people is they take vacation, they have family, they have children, those priorities get in the picture. So right about the time we were going to drill, the guy says, I'm going to be on vacation. And this is the guy who had 50 years experience. You really were counting on that person's experience. Or, I don't know why, people get sick. So the drilling engineer is supposed to be at work 6 o'clock in the morning, and he's sick, he can't come. So the way the system is going, we're going through a tremendous amount of automation and robotics, where we figured out that probably 70, 80, in some cases 90% of the thing can be done automatically, because you still depend on the engineers to make the final decision. But you can remove that burden and that dependency in many cases. So you could have sensors here to recognize that the well should be shut in. You could have sensors that says water is coming, we better stop that. And this kind of thing is going on. This room and the next room and the facilities we have here is part of it called CSTOP. This is the unique center in the world for that matter, the Center for Interactive Smart Orbit Technology. Chevron established that as one of the few companies very early on. And the whole idea was that what happens if you put lots of people, we have 22 faculty, about 42 PhD students, and a whole bunch of masters working on research related how do you do this automatic robotics, the sensors and all that. And there's a lot of problems involved here, as I told you, such as the signal transmissions, the distances we're working with. But we're getting there. We're getting to the point, honestly, you could be in San Francisco and actually observe how they're drilling a well in Trinidad and how the seismic is looking in China. And if you're an expert. So this is even better. It depends on you to make decisions on something that's happening, continents away. Of course, here we need a lot more smarter people who can analyze this thing remotely without touching it, feeling it. Just the way, as you've heard, people are doing surgery remotely. You could be in New York do surgery in California, you heard about that. The same thing is happening here. That you be able to drill without actually being on the site and have the confidence that what you're doing here, the robots will do it for you. So the field of robotics and information technology is really taking over this business and making it much more reliable, both from the standpoint of cost and reliability, safety, the environment, and safety of people. I want to show you the limitation I was mentioning to you about placement of platforms. See here, this is a shallow platform. When you go a little deeper water, you cannot use the platform. So you use what's called a spot. Spot is a place where you could have people walking and working and everything. However, it's kind of a floating device, and you've anchored it. When you're done, the spot is there, and you have this conductor within which you have all of the wells you drill. When you go here to greater depths of water, you put a drill ship, you drill the wells. When you're done, you complete the wells right here and walk away. And there's nothing left at the surface. And again, it shows you the evolution. The fixed platform, if you look at basically the floating production, then tension leg platform, and of course you go into the spar. This is the typical picture of a platform. Now, our students, you should go on a field trip and they see that. You actually have to see the technology that's in the middle of the sea. How much, this is mechanical engineering, this is civil engineering, this is chemistry, this is chemical engineering. You got to worry about corrosion, you got to worry about the stress calculation, you got to worry about electric supply that this thing needs. You have to make it independent. But I tell you, if you ever live on this platform as an intern, it has the best food in the world. Just to make sure that the employees don't complain, because there's nowhere to go. And the cafeterias are open 24 hours, the pool tables are open 24 hours, just to make sure. They work on a shift. So you're there, say, 12 hours, and then you're off 12 hours. And in many cases, actually, you work 20 days, and you're off 12 months. When the actual drilling is going on, it's a very exciting place to be. I'm sorry. This is another picture. But actually,
it's like Party City.
It is. And here, actually, you can see that there are barges next to that. We're getting to the point that in many cases, we don't bring the crude oil to shore. We actually process, and we basically load the tankers right there and tankers leave. So you have no idea something is happening down there. Now, This is the way things are being developed again. And so you remember you're coming down and you're branching on a number of wells, and of course all of that is being completed at the seafloor. Here's another picture. This is happening. This is another science fiction where, again, if you look at the bottom of the sea, you have different, these are names of the structures in the North Sea. You can see actually the bottom hole location, how the wells are, and then you're able to, again, by the time you're done with all of that, there's nothing at the surface. You simply have a flexible pipe coming to the tanker, the floating operation, that will really, you can load it with whatever crude or whatever you're producing. Yes?
Oh, what did that subsea, the part at the very bottom, what does that do?
So what you have is, in many cases, okay, if you're an on-land operation, you produce, you get to a point there's no more energy, you put a pumping unit and all that. But imagine this is subsea. You can't go put a pumping unit there.
Yeah.
So you plan that for the first 5 years, this may produce by itself. But I got to prepare for it. That when the pressure goes down, what am I going to do? So on day one, you put injection facilities. You put water injection, water pump, all kind. In other words, you predict for the next 30 years, what do you need down there? So right on the seafloor, you have all of these facilities that will support that. You may not use it day one, but when you're ready to do, everything is ready for you. Yes?
How do you get away from the rust?
Good question. We have in the field of chemistry a technology that calls cathodic protection. The idea of cathodic protection is that the reason you come up with corrosion is because you create like a battery condition that you start eating. So if you have a sacrificial cathode someplace, for instance, you can put a piece of metal in the water, and you make the current in such a way that rather than eating the platform, eats that piece of metal. So what the heck, so we're going to put another piece of metal there. So using the cathodic protection, we prevent that. And these structures actually, you won't believe this, so I'll tell you a number. I'm right now working on a case that I was a little worried about how long that. The platform that has been operating in Santa Barbara for since 1973, they were proposing to do something, and I'm doing a little consulting on that. And I said, is this going to last? They said, yeah, it just went through a 1,000-year certification. That means that structure is going to stay in the water. Of course, they're not going to be there 1,000. Yeah. It hasn't lost anything. There's been no corrosion, basically. Okay? So, now, it was mentioned today, and I'm going to spend a little more time on this CO2 later on, the whole question of how do we deal with the carbon dioxide. Carbon dioxide is a gas that we don't want to add into the atmosphere to the extent we can. The question is that can we, as we produce oil, as we burn it or gas, can we return the carbon dioxide back in the same reservoir? And this is being done onshore and this is being done offshore. Because what you have in the reservoir, again, is a storage. It's true that the storage is in between these pores, among all these little tiny holes that you have. But the same place that contained the oil now is empty, so you should be able to return it. There's this going on actually offshore that allows you to do that. I'll spend more time talking about it. We talk about remote operated vehicles undersea, because I know some of these robotics person, and this is how it is. So as I said, in order to be able to go and fix a wellhead, seafloor, you actually have these vehicles that are remotely controlled, that they go and they do all kinds of mechanical things. And so all types of robotic manipulators are now used for operating as such water depths. And then typical offshore operation in the past has been you produce, you build a pipeline, you bring a crew to the shore, you process it, and you sell it. You go to Santa Barbara, you see a whole bunch of that. But now, you're coming up with this thing that are self-contained. So you can actually do the production, remove the water, remove the gas, and then be able to actually load it to a tanker without bothering to build a pipeline. Because, you see, building a pipeline between shore and a structure is, 10 miles is okay. 100 miles, very expensive. Not only is it expensive, you have to worry about the navigation, all the tankers and the ships basically in the channel, and making sure that there's no accident. I'm giving a story. In terms of communication, before we went to this wireless thing that I was talking about, for the signal communication, the company started using fiber optics in the Gulf of Mexico. So they invested heavily to put this network of fiber optic line, and they would rent it to different companies. And it turned out one of the fishing boats started cutting the whole thing. You have to be very careful when you go underwater, who might be interfering with your operation. Now, these are typical control rooms and this is becoming more and more popular in the sense that, for instance, you take a room like this where you could have a reservoir engineer drilling to a production engineer, communicating with the people at different locations and bringing all of the smart ideas they have to be able to remotely decide what should be done next. So this is called the collaboration room. Most companies these days have collaboration rooms. And I am working, one of the projects that I have is on the training of people for these rooms, because it's easily said than done. If you put people with different languages, different culture, people who have different types of education, somebody went to Indonesia, petroleum engineering, somebody went to China, somebody went here, they can't even speak the same language. It's almost like flying an airplane and dealing with the control system, making sure that they all follow the same process. It's not an easy thing. And so the training and being able to do that remotely by itself is something that needs to be done. So what all companies are doing, all of them, they realize that it may be difficult to deal with established people or older people, because these people are already conditioned to do things certain ways. So training of the younger people, by the way, this is not just for oil business, this is for hospital business, it's for everything. Training of the younger people to work in a collaborative atmosphere is becoming an important area of research. That how could you train people? Remember the way we reward you in elementary school, high school, university. It's always missing. There's 20 people, one of you is the best, right? The other one is the second and third, fourth, right? First runner-up, second runner-up. In that kind of a system, you compete with each other, which is good. But at the same time, you don't learn collaboration. For instance, we put our students to work in this science project or in the laboratory. 3 or 4 of them are lazy. One finishes the job, submits the report on behalf of the rest of them. That's what I said for your project. I want to make sure all of you work. So how do we change the reward system that you work as a team? Because if you don't learn it in elementary school, high school, college, you're not going to do the work yet. Everybody wants to dominate. Everybody says, my way is right. And so it's a very difficult thing to put a reservoir engineer or production engineer drilling. Same thing in hospital. Difficult to put a bunch of medical doctors who come from different training to decide on an issue that's remotely located. The patient is dying and they want their opinion. Everybody has an opinion. How can you come up with that? But everybody wants to get credit. It was my idea to save a life. And that is becoming part of the education, I guess. How do we design problems? How do we do that? People get trained. So, just show you that you begin, once you start working on a field, you begin to feel this part of your bloodstream. Think about it, dream about it, and you plan for it. And of course, we have all types of immersive visualization systems that makes that possible for you. The job of a reservoir engineer is to find out how much oil is there, how much water is there to push the oil out, and the compartments. Compartments means that you could find a portion of the field that has one kind of a crude, one kind, another part, different types of a crude. So we have to be able to map it. This is the example of what I told you, the multilateral. This is how we drill wells. You come down, see that? Level 1, level 2, level 3. And so with one well, then how could you do that so these things don't get mixed up? So you have a remotely operated valve, and that by itself is a fantastic technology. How you can control each branch. So the mathematics of designing, making sure these wells don't intersect each other, is a part of the drilling operation. And again, working with the images you have from seismic and designing that becomes a combination between drilling engineering work and reservoir engineering. Again, these are some additional images of how you come up with a representation of what is underground. Now, Mr. Williams mentioned this morning about the Gulf of Mexico, Louisiana, Texas. If you ever fly with a helicopter, you'd be amazed how many structures are there. Each of those dots that you see is actually a structure. There are hundreds of wells that have been drilled over there. And if you are working close to shore, it's fairly easy. But the minute you start going 50, 60, 70 miles, there is really nothing out there. You become kind of interesting to see how these guys actually locate, as I said, the structure. So the helicopter rides, as you may run out of fuel. So what they do, you have the platforms, and you have flat areas that's like a landing. So if you get tired, you can just land and relax and have a cup of coffee and then fly again. This is how interesting the whole thing is. Now, the problem that we're facing is the certain bad times of the year where the weather is such, like you heard about it. Yeah.
How would like oil companies or just energy companies get permission to be drilling into international waters?
Very good question. Question is, how did the oil companies get permit to do that? Okay. Just draw a picture for you. The United States is the only country in the world where people on land own the oil resources. In other words, if you live anywhere in California, and if you hire me, if I can find oil for you, that oil belongs to you. Nowhere else in the world that happens. Oil belongs to the government. Okay? So let's look at California. Anything you find here on land, except if there's federal land, it belongs to you. Okay? And there are people, if you go to Huntington Beach, even Redondo Beach, we had some old operations. So Huntington Beach, Long Beach, you might be getting a check at the end of the month. You're not even doing anything because there's an oil field under your house. Okay? So what we do, we divide the ownership into what we call surface ownership and minerals. So if you were, say, 50 years ago, when you bought a house, you own the land and you own the minerals. It's possible that sometime in the history somebody came and bought the mineral right from a previous owner, so all you own is the surface right. So if you want to buy a house, take a look whether you own only the land or also the mineral. If you own the mineral, whoever drills to produce here, you get a share of that. Okay? This is for the land. But how about water? For 3 miles, belongs to the state of California. Beyond 3 miles, belongs to the federal government. So if I'm an oil company and own some land or something like that, I can operate here. All I need is the permission of the surface owner. If I want to say there's a structure, I want to drill here, I have to have permission from the state of California. If I go beyond 3 miles, I have to go to the federal. What they do leasing. So they do a lease sale. They say, okay, on such and such day, we're going to have a lease sale here. There's seismic done over here. They know where the structures are. So you go submit bids. I put an envelope that says $10 million bonus. So put the $15 million. We don't even know what each of this envelope. They open up, whoever has the highest bid gets as high. So the Gulf of Mexico Minerals Management Service, you probably have seen that logo here, which is part of the Department of Interior. They manage those lease sales. And so anytime you see something over here, in fact, you can see over here, 86 by major oil companies is part of the lease sales that they have. And the red ones are by non-major companies who bid on that. And of course, these are very, very expensive operations. And it was, Chevron had, for instance, the discovery a year and a half ago called the Jax discovery. And in that one, Devon, a small company, also participated. But investment in these things is a minimum of 3, in most cases $10 to $12 million for one operation. And so when you get involved in that, you sometimes bring other interest owners so you can share the risk. And of course, if you make a discovery, then you pay all of the production, the percentage to the government, the rest is for you. If you're on land, you only pay a percentage to the surface owner, the rest is you. Okay? So that's how it goes. Did I answer your question? Yes.
How much damage do they take from weather conditions and hurricanes?
Yeah, I was just actually, before I started, I was saying this. You remember the Katrina situation. So what happens over here these platforms are producing. A typical platform here produces 50,000 barrels a day. Okay? Imagine you own one platform producing 50,000 barrels a day. Now, here comes a hurricane. What do you have to do? You have people working there, right? You have to evacuate them way before that. And you have to shut down the platform. For a week, you're going to have problems. 7 days times 50,000, that's 350,000 barrels. If the oil was $100, figure out what the loss you have, right? So we got to the point that there were tremendous losses because we have to shut these things down. Now, gradually, most companies are getting to these remote operations. You evacuate the platform, you keep the platforms open, you operate. It doesn't matter what comes. As long as the structures are strong enough to hold, and they are. So the incentive to use robotics and remote control is just to make sure you don't have to shut things down. Now, U.S. actually was asked this morning by Gitmo.
If a hurricane hits, does it ever actually knock the structure over and
Yes.
lead to an oil
Yes,
spill?
absolutely. In a case of it. You see, what happens is, it's almost like any other operation. You design the structures to last a certain amount of force. For instance, in Los Angeles, Similarly is designed the buildings to last an earthquake of, say, 7.5. Okay? And truly you can do that. But then you get surprised, you have 8, so the structure cannot last. So what they do, they look at the hurricane for the last 100 years. And then they design it, they call it the 100-year average. And if something comes way above that, it can kind of surprise you. Now, of course, now they're using a factor of 2. They're going for twice as much as what the average of the century has been. There have been a few cases where the structures were not designed properly, and actually the hurricane actually uprooted the platform, and they lost the platform.
When the platform's uprooted and stuff, does the oil spill into the ocean?
No. Let me show you here. So this is the surface of the water, it's the seabed, it's the structure, and let's say that you have the riser here, then you have, let's assume this is just a fixed platform. Over here, so this is the platform, sitting right here. Say for any reason this wasn't designed properly. Anytime a vibration happens more than what's necessary, you have valves right inside the pipe that shuts the whole thing down. So if this thing is all gone, no problem. This shuts down automatically. There's nothing coming. Now, of course, later on you decide if there was a substantial amount of reserve left here, you actually build a new one. You go here, you connect. You find out it's not, because you do the economics. Okay, so about a million barrels left, it's not worth it. Then you just go ahead and pump cement down here and abandon it and walk over. No, there's no danger like that. So, I think your name is Jimmy, right? Yes. Okay. You were asking about why do we drill in the U.S. So this shows you different areas of the country where we have oil fields. You can see that California is actually number 3 or 4 nationally. Then, of course, you go to Texas, Oklahoma. You have some small operations here, and of course, you go to Louisiana, and of course, you go to the offshore here. California offshore, we have lots of resources that are in moratorium. Since 1960 now, we are not able to drill new areas. All that can change. But onshore, it's a very fertile area for oil and gas. So we do have oil fields, and of course, many companies, especially small companies, going back to get the rest of the oil that's left in these reservoirs. So this is the oil and gas fields, and this is the basically gas production again in the Gulf of Mexico. You can see in different areas. This is the field that produce what we call conventional gas, just to produce gas. Now we get into areas where we have what's called unconventional. The rock is so tight, nobody would have imagined you could produce what you're producing from that. And so this is the tight gas place. Use the word place. This is interesting that, for instance, you go to the Pennsylvania area, you could drill almost anywhere to that you find gas. It's very tight, but you fracture, you get a gas pump. These wells cost about $3 million. Lots of people that I know, they participate in this drilling, because there's no risk. Anywhere you can drill, you find. It costs $3 million to drill a well, and you get your money back about a year and a half, and after that it's profit for the rest of life. So many people have got into this business that all of a sudden the gas production in the U.S. is going up, which is very positive. This is the shale gas. Again, you see this area. You drill anywhere. You don't have to look for a structure. You don't need seismic. Anywhere you drill, you find gas. Okay? Barnett over here, Marcellus shale. And of course, since was talked about coal, the coal that most of you know is the coal that's at the surface. We do mining. But in many places we find coals that are very deep, so you cannot mine them or extract them. But we use them like a petroleum reservoir. We drill a well, we dewater them, and all of a sudden the coal becomes like a gas field. You start releasing gas, and it becomes like a gas field. It's called a coal-based method, and that's also becoming a major area of investment. It was mentioned by Down that because of the advantages that natural gas brings to the market in terms of being a clean burning fuel, lots of interest in natural gas. And if you look at where are we going to get our natural gas, you will see that, of course, we have some discovered fields. Now we're going into the domain of undiscovered. Now we're going to go to the area called the geopressure. These are areas where there's a lot of water, water-dissolved gas. And then, of course, it was mentioned the hydrate. This is an unknown right now. There are many areas in the U.S. actually that you can drill and get to hydrate. This is like a frozen methane. It's water and methane. If you are able to get that methane out without sinking the land, for that matter, which is kind of tricky, there's gas over here that will last forever. And but there are technological problems here, and there's lots of research going on here. How do you separate the gas from water without causing damages to the formation? Now, these are as I mentioned, we're going to focus in this camp for the U.S., but I think it's important for you to know how do we measure up the rest of the world. If you look at the proved oil reserve, and I should mention the word reserve. Reserve is at the current technology and the current price. Price goes up, reserve goes up. So you can do more things. Price comes down, you can do less things. So the current prices you can see here, and this is 2004. If you look at Asia Pacific, these are in terms of a million barrel. 41. North America, that's U.S., Canada, part of Mexico, basically, upper part. And then of course you have the Central South America, 101. Africa, Europe, and the Middle East. That's where the problem is, you see. So about 75% of actually reserve is in the Middle East, all those countries. And the problem becomes transportation. Transporting oil, we have a solution. You can bring it to a tanker. Transporting gas is difficult. So in many cases, they squeeze the gas, they compress it. We call it LNG. You put a tanker bring. And you probably have read in the news that there's a lot of opposition to building LNG facilities in Long Beach. But fortunately, with this unconventional gas coming out, we're getting to a way that we can satisfy our needs from the gas company. And then this is the proved natural gas resources. By the way, let's go back to that slide. Let's just stay with that. Suppose starting today, we're not going to do any more discoveries, no more research, nothing. Can you calculate for me how long this is going to last? This is about 1 trillion barrels. Today, we are using roughly about 80 million barrels a day. Okay? How many years will it take? So no more discoveries, nothing. Just using at this rate, no more population, no more babies, nothing. Just stay at where we are. 80 million barrels a day, you have 1 trillion barrels. So a year, if you take a year is 365 days, used to be, right? 365 times 80, how much is that? 365 times 80. Come on, you guys can do it in your head.
That's short of 3,200? 32,000.
3,000 what? 3,000 million, that means 3 billion, right?
Yeah.
Right, is what you're saying.
2,000 so 2,000.
365 times 80, and then million.
So roughly 32.
32 years?
32.
33 billion?
32,000 million.
33,000 million?
Yeah.
That was 33 billion, right?
Roughly, yeah.
So if you take 1 trillion divided by 33 billion, how many years?
Couple hundred? 300?
30 years.
Like 20 years, right?
About 20, 30 years. So some people say, we're going to run out of oil in 30 years. That's only what?
It's only based on what we have now.
And it's funny, if you go take a look at the statistics about 20 years ago, we have almost the same numbers. So what happens? We are constantly discovering new resources. In fact, roughly the same amount is out there which we haven't explored, but we know geologically is there. So that's 30 years, what do we do? 30 years, another 30 years, 60 years, okay? Now, this assumes you're not going to go after heavy oil or tar sand, because there's a tremendous amount of tar sand and heavy oil. Go after that, it very easily brings us to the next section. So that's why I'm trying to think of resources, you have the oil to get this.
Why does the Middle East happen to be so oil rich compared to the rest of the world?
Excellent question. So, there is the video, if I can find it, we'll make sure that Julie will share it with you. We have this concept called a plate tectonics. You may have heard about it. Okay? There's a video that actually shows you how these continents were all together, and then they separated, they are where they are. And when you look at that, you can see that some of them are underwater, some of them are above water. Every part of the world that was underwater, you had a better chance for formation of deposits that later on became oil fields. Every part of the world that had more volcanic rocks, it has less chance to be a good host to organic material. Okay? So, excuse me, you go to certain parts of the world where the rocks are very hard, volcanic, there is no oil. Go to parts of the Middle East that this whole thing was underwater. For instance, Iran, I'm from Iran. The southern part is one of the regions that have been discovered that based on that has about 120 billion barrels per day. There are 6 other regions in Iran that haven't even been explored, but geologically they contain a similar amount. Okay? So, and maybe one of these, I'll show you a map. It really has to do with the type of the geology that exists there. And it's funny, when you look at the fields that have been discovered in Iran, Iraq, Kuwait, Saudi Arabia, it just follows a very fantastic trend that you say, I could have discovered the next field because they're just next to each other. You just line up. And then so, now you come to California. California, it was, where you're sitting here was underwater years ago. We have to clean it up and build it through. So this is, in California, all the way here it was underwater. Okay? So gradually, in the geologic history, we have periods of time that either the water comes up or the water goes down. So we are in a position that the water has gone down, and this area we live, but then there are areas here that was underwater, and they before water. So along in California, we have fantastic amount. I mean, this rock that I showed you, the soft one, that's called diatomite. That happens from Baja California, along in California, all the way out to Oregon, Washington, going all the way to the Pacific Rim, all the way to Japan. Okay?
Oh my gosh.
So this is how it is, it's a scale of things. So this is a very rich environment over here. You go to Texas and Oklahoma, there are reasons that there are certain type of field there. All of the offshore areas, the potentials are good. You go to the Middle East, the whole thing was underwater. So it really depends. So what we do these days, let's say if I want to find oil in Honduras, what do? And I can't even go on land, covered vegetation. We fly this the airplane, very low-flying airplane. Let's find out the magnetic field. Areas that have very high magnetic susceptibility, they probably have volcanic rocks. I don't want them. Areas that have low magnetic susceptibility, they're probably are sedimentary rocks. Then I really gravity there. I find the density of the rock. Rocks that are volcanics are not good. Rocks that are lighter are good. So if I find under all this vegetation that the rocks are sedimentary, then I send a crew to clean the trees and start drilling, do the seismic, and I find, that's how we do it. We perfected the technology where to find it. On land is fairly easy. Okay. Offshore is a problem because now you got 10,000 feet of water, you got to figure out how you get there. And it's amazing with the seismic technology we have, we can't even find structures. So if the price of this commodity goes up, people are willing to take the risk and go deeper, deeper, and deeper offshore. If the price goes down, for instance, Chevron, as a big company, last year they were going to drill about 2,800 wells in Colorado for natural gas. And the price went then, they stopped that. So the level of activity has to do with whether or not you can make a profit on that investment or not. But eventually, I think when the demand for this product goes up, and notice that from Dr. Sheikh's presentation, it's not just the transportation. You notice all of the things that come from hydrocarbons. When the demand goes up, people are going to be exploring all over. I mean, the work in India has just started. The work in China, they gave up on land, they're going offshore. Okay? So there's lots of opportunity to be able to explore. But what it is, it takes technology, it takes smart people to be able to use these technologies. Very complicated, actually. So this is the natural gas. We measured the natural gas in different units. The units I was talking about, the MCF, we use trillion cubic feet. Here we're doing the trillion cubic meters, which you have to convert. Again, as you can see, between Russia and the Middle East, that's the highest concentration of natural gas. We have enough natural gas in the Middle East and Russia that will last 400 years. Only if we were able to bring them to areas where the consumption is high in an inexpensive way. Only if we can improve the LNG technology. We'll quickly go through the carbon sequestration. So any type of the fuel that has carbon, when you burn it, you're going to create CO2. Sequestration means you'll be able to store it somewhere. One of the places is exactly the place where you produce the hydrocarbon, in oil and gas field. Okay, so that's, now, I will just show you that no matter what the fuel is, you're going to get by the time you burn the fuel, you'll heat the water, you're going to do it. Now, the question is that, does burning of the biofuel also, or biomass generate CO2? And the answer is yes. Anything that has carbon will generate the same thing. This is an animation to show it here. Now, this morning there was a question, this is nothing to do with oil and gas, about the clean coal technology. As Dr. Paul indicated, we have plenty of coal in this country, and coal can be a source material for plastics, could be used for generating natural gas, you could liquefy it, transportation fuels out of it, only be able to clean it. A part of the cleanup is CO2. Part of it is SO2, basically, that coal seams, they do have sometimes sulfur. Sulfur is the worst thing that you can deal with. Because if you're burning coal and of course you get the gas and the water, SO2 and gas, water mixed up, you get what's called a sulfurous acid. And this is the one that they call it acid rain, that it gets into the atmosphere and causes damage to the building, corrosion, all that stuff. So now the clean coal technology is to get that sulfur out. And there are various ways to do that. For instance, they pulverize the coal, put it in this flotation cell. All of the metals and heavy metals and all that, they go to the bottom, and then the coal, which is lighter, stays top. There are many, many ways to do that. And so there's a lot of research going on in terms of how can we, because now we have all these resources, how can we take the coal, remove the nitrogen, remove the SO2, and make it clean. That's called the clean coal technology. And of course, there's a lot of effort going on to, see, coal has a shortage of hydrogen. But if you put it to a proper combustion with water, you can generate methane out of it. So someday we're going to get to the point that we will not burn the coal. We will convert it to methane, and then we just use the methane for that. Okay. Again, these are some experiments in terms of how you could basically sequester the CO2 that you have and use it not only to store it there, but even push the oil out. CO2 mixes up with oil and it increases the recovery. So this is the double benefit from that, storing it and producing it. Now, this idea is called the zero carbon footprint operation. Most of the major companies have pledged that by 2050, they will have zero carbon footprint. That means the operation will be such that you don't get even an ounce of CO2 getting out. It all will be closed where by the time you're done with the operation, the CO2 stays there, all of the oil and gases come out of the store. Okay? And again, these are additional examples about how you would do the sequestration by storing it underground. There would be a presentation made on Wednesday at the biofuel. No, on the chemistry. Tomorrow? Wednesday. From the chemistry department? No, on, what's his name? For Prakash.
Tomorrow.
Tomorrow? Okay. So you're going to hear a fantastic presentation by, you all know Dr. Ola, who got a Nobel Prize in Chemistry. He has come up with the idea of what they call methanol economy. The idea is that rather than sequestering the coal, having the CO2 by pumping it underground, you can take CO2 and make methanol out of it. Now, how many of you know what methanol is? You have taken chemistry. You have the methanol and ethanol and propanol. Just depends how many CH you have. So ethanol has C2H5. Methanol has C2H3. And propanol, that's the rubbing alcohol that you did, has C3. So ethanol is the alcohol, regular alcohol that you know. Some people drink it. It damages their system. Methanol is poisonous. If methanol gets into the water system, or that thing that happened in 1979 where people were siphoning gas from each other's tank, you smell methanol, it kills you. Okay? Methanol is very dangerous. However, his idea has been, if you take the CO2, you can convert it to methanol, which is true, with a little hydrogen. And then we run our cars with methanol. The objection to his case has been purely based on environmental, that that's a very dangerous substance. So when this professor we invited to, he's not Dr. Ola, but is one of his associates who's going to talk, hear what they're talking about here, and then question him on the question of the environment, what can be done in terms of the toxicity of the substance. So that's another way of getting rid of CO2 if you can come up with a way. Of course, my idea would be get a methanol converted to ethanol because you can. Then you have regular alcohol, which is a better thing to do, but I don't know how about it. This is showing you how the injection of CO2 that you're using to be sequestered actually would help to reduce oil. The last thing I want to talk about here, and we're getting close to that, is geothermal. Just the way that surface manifestation of hydrocarbons shows you there is oil on the ground. You've been to Yellowstone, how many of you have been there? You see the steam coming out of the ground. And so that's an indication there's something hot on the ground, and that's just what we call geothermal. If you go to the Northern California, you see wells. If you open them, you get the steam out of the ground. Fantastic sign. Because this is clean energy out of the ground. Steam, high pressure coming. All you have to do is put a power plant and convert it to electricity. That has been done. So in some cases, the steam comes up, goes to the power plant, you make electricity. In some cases, water comes out, hot water. You extract the heat. You pump the cold water back. You extract the heat. It becomes If you drive about 30 miles east of Reno, you see these small operations. These are, believe me, mom and pop operations. You have two wells. They just rent an area. They drill two wells. They have a small power plant, and they produce one, make electricity, pump that one back. They're not even there, and they sell the electricity to the utilities. Why can't we do this everywhere? Because you don't find that heat source everywhere. There are certain parts of the world that the heat source is close to the surface, but the geothermal grid is how you can use that. So the limitation on a geothermal is that it's not readily available everywhere in the world. And so that's really how it is. As far as the drilling and the reservoir is exactly what we do for oil and gas, except here there is no hydrocarbon drilling in the well. Now, in some cases, the temperature is low. For instance, right now, if you go under your house and drill a well, you go about 10,000 feet, you get a temperature of about 150 degrees. That's not enough. But people are working. Can we extract the heat from 150 degrees and make power for home? Yes, if you can come up with some sophisticated binary system. In a binary system, what we do, we take that heat, we evaporate in a closed loop, low boiling temperature fluids such as isobutane, and the isobutane turns the turbine, and the generator to make electricity, you pump the thing back. Currently, the technology is at 220. We haven't come up with a technology that will go to 150. If you do that, you could have a geothermal power plant in your home, and don't worry about Edison PG&E to sell you electricity. But we haven't got that. That's an area of research. In fact, we just hired a professor who's writing a proposal to work in that area. This shows different areas in California where you have geothermal resources. The most interesting part is this area, the geysers, the north of San Francisco. Fantastic area to visit. And of course, you go to Imperial Valley. You have the Mammoth. If you've gone to skiing there, you've probably seen some geothermal power plants there. And so California is really blessed. Not only has an agriculture industry, it has a software industry, it has an oil industry, it has a geothermal industry. It's a blessed state. The use of geothermal doesn't have to be making electricity. In many cases, where the temperature is not high enough to make electricity, we use it for heating, home heating. And so basically what you have is you have a pump that sends the water underground, extracted heat from the ground, comes here, and then you have heat exchangers. So you can heat the home without necessarily using electricity. I'm showing you these ideas for those of you who come up with alternatives by Thursday. Think about anything like that. And then the last thing, again, I should mention here, you heard about oil shale. We have, again, U.S. has tremendous resources in oil shale. The only company that has invested zillions must be bigger than billion, and this is Shell Oil Company. Shell has perfected the technique. It's really a fascinating technique. But the concern about shale oil was that you have to actually take the rocks and you heat them up, extract the oil. The technology they have, you drill the wells, and then you raise the temperature down there, you extract the crude oil without really destroying the environment. They've patented that, so if you want to read about it, you may even find a series of slides on the internet. Look at the shale oil and the Shell Oil Company, SHE-double-L. And so that's coming up. To see where we're going in the U.S. As far as the liquid oil, the companies are focusing on shale oil, heavy oil, tar, coal liquefaction, and as far as the gases, coal bed methane, shale gas, pipe gas, these are what we call unconventional resources. Reality check. You'll realize based on what I showed you, and at the speed that we are developing alternatives that are cost effective, we're going to be stuck with the hydrocarbons. So all we have to do is come up with ways to make it zero carbon footprint, no CO2, and that's a very important area of research. Again, this is an advertisement and a bunch of things I could probably mention. I just wrote it for you. That first link is very important. EIA, Energy Information Administration, has all kinds of statistics about U.S. and the rest of the world, about consumption, about where things are coming up. The Department of Energy has a site, fossilenergy.gov, that has all kinds of materials for you. And then also California has this page, which is mostly for schools, teacher resources. But you're going to get some interesting information about different sources of energy. So I hope you will have a chance to visit this as you put your stories together. So this was a kind of an overview about resources that are underground, that have been helping us and will help us for the next 100 years until we come up with some better solutions. Okay? Any questions? You're tired. You had a whole day of things.